All right, chapter 3, section 2, graphing f of x equals ax squared plus c. So really there's only a subtle difference in this section from what we did in the previous section. And this will actually look very, very familiar because in section 1, we basically did just that, ax squared. And again, just to kind of give us a refresher, because it's worth doing in this section, there are two things that this a will do. Okay, so this is a little review from section 1. This a, this coefficient to x squared, is going to do two things to the shape of a general x squared graph. Okay, and so just to remind us, x squared is going to be what we call a quadratic function. It's going to be the shape of a u, also called a parabola. So we know we're going to get that kind of curve just because there's an x squared. These a and c are going to change the shape and location of it. And so to remind you, this a is going to change the shape in two ways. Way number one, it's going to change the steepness, okay, the narrowness or the shallowness, the steepness, whatever you want to call it, the steepness of the parabola, the quadratic function. So for instance, whatever u shape I'm dealing with, the bigger that number is, okay, big numbers like 100, a million, 82.567, whatever it might be, large numbers, okay? Large numbers will make this steeper, just like it would for a slope of a line, okay? It's going to make it steeper, more narrow. The closer this number would be to 0, like small decimals or fractions, like 1/2, 0.0236, okay? Small numbers, the closer it is to 0 is going to make it more shallow, wider, that sort of thing, okay? Just like the slope of that line would be a very, very shallow slope. Okay, so a is going to affect the steepness of that curve, that quadratic, that parabola. Okay, the second way that a is going to affect it will be whether or not it's happy face opening upward. If it's positive, if a is a positive number, it's going to open upward like both of these guys. Okay, if a had been negative, any negative number, however big or small, it's going to open downward or be sad face. Okay, both of these were positive A's because they open upward, but a negative A would face downward. That's what we learned in section 1. How did A affect this x squared graph of a parabola, this quadratic, that U shape? How does it affect it? And it does it in two ways. Okay, steepness and whether it opens upwards or downwards, happy face or sad face. Okay, what we're going to learn in this section is what does C do to that graph? Now, A is still going to affect the same exact things on an x squared. It's going to affect the steepness and whether it's happy face or sad face. This C is going to affect position of that graph. Okay, namely, and here's really the punchline of this whole thing. So if you're taking notes off to the side or in the margins, whatever it might be, basically what C does is it takes that graph and it moves it up or down. And that's basically it. Okay, so for instance, in these two examples here, that x squared, that general parabola, and technically there is an a in front of that x squared, it just happens to be 1. Okay, but that +2 tells me that I'm going to take the x squared graph and move it up 2 units. And you can see that here with the vertex, how it would have been on 0, 0, but that +2 took that vertex and moved it up twice. So that's the new position of that x squared parabola. In this one, since it was -2, it moves down 2 units. Nothing really super exciting happening here. Basically, whatever value C is, if it's positive, that tells me how many units up the graph moves, or the vertex more specifically. And then if it happens to be negative, that just tells me how many units down it goes. It's no different really than reading a coordinate point. Okay, and so that's essentially what the C does. Okay, you get a couple of examples here just to kind of briefly discuss these. Here in part A, I just have an x squared. Again, technically there is an a multiplied by that x squared. That a just happens to be a +1, so we don't bother writing it, right? Now the C, this other value that's subtracted from the x squared, that -3 is simply going to mean that I'm going to take the original parabola that would have been for the x squared. I'm going to move it down 3 units. Okay, so what would have been the x squared, the vertex would normally have been at the 0, 0 mark. I'm going to take that and move it down 3 units. That's what that -3 means. Okay, and I'll show you that result in just a minute. And then this last one, okay, there's a little more going on with this example. Okay, the part I want you to focus on today will be that c, the plus or minus that's after the x squared right here. So that +1 simply means that whatever we would have done in section 1, I'm going to take that result and move it up 1 unit. It's going to move up 1 unit. That's what that +1 means there. Again, just to break down what that 4 would do, this is more of a section 1 type of result. In section 1, we learned that because it's a +4, it's going to open upwards. And because it's a 4, it's a bigger number than the 1. That means it's going to be a little more narrow or steeper than the regular just x squared graph would have been. Okay, so really quickly, just moving over to the solution sheet just so you can see this graph and kind of see what kind of work I'd be looking for, what I'd be expecting on a test. These first 2 examples represent both of those problems. Again, part A, we were given this quadratic function, x squared -3. Again, I know it's a quadratic. I know it'll be a parabola. I know it'll have this U shape simply because it's an x squared. The -3 took what would have been, and you can see lightly in pencil I drew here right there that what would have been an x squared graph, very lightly drawn right there. And then it took that x squared, and because of that -3, it dropped the whole parabola down 3 units. Okay, I'll talk about these zeros in just a moment. But to again show what kind of work you would see, this is very similar to what we saw in section 1. You would create an XY table. You can get away with only doing 3 coordinate points because that's really all you'd need to see where the parabola opens up or opens down. And so again, having a negative value, 0 value, and a positive value are useful here. And in order to show the work, whatever I choose for x, I'm just plugging it into whatever the function is. This is just a little busier than what it was in section 1 because now I have to subtract 3 at the end of it. Really just be aware of your order of operations. I have to deal with the exponent first. So when I plug -1 in, I have to do -1 squared first. So that's -1 times -1 or +1 now. And then I would subtract 3 from that +1. I'd get -2 as a result. What did that -2 mean? That literally created a coordinate point, -1, -2. Okay, coordinate point -1, -2. I would plot -1, -2, and that point would be on my parabola. I would do the same thing for 0 and 1. Again, just be careful with order of operations. You'll get coordinate points as a result. We would have graphed these 3 coordinate points right here, and that would be enough on big ideas to show where the parabola would be located. And as you can see, the vertex has dropped 3 units from where it would have been in section 1. Okay, that's what that -3 did. And then in part B, there's our 4x squared plus 1. Again, it's a little busier, even more so than the last example. But again, when I create an XY table, I'm just plugging values in for x. Just make sure you show your work. This is now, again, a practice in order of operations. I have to deal with the exponent first in PEMDAS. So in this case, when I plug in -1, I do -1 squared, or -1 times -1. That would give me +1. Okay. So then I would do the multiplication next, the 4 times whatever I got for x squared, in this case 4 times 1, that would give me 4. And then I'd add 1 as the last thing. Addition is one of the last things you would do in PEMDAS. So the 4 plus 1 would give me 5. And again, what we've created is a coordinate point, -1, +5. So I would graph that coordinate point, and that's what I would get on my graph. And so I would go through the same thing for plugging in 0 and 1. Just be careful again about your order of operations. We would get these 3 coordinate points once we graphed it. Again, big ideas, that'd be enough for us to overlay that parabola inside of it. Comparing it to an x squared graph, just like we did in section 1, and lightly in pencil, I drew the regular x squared graph here. You can quite obviously see that this new one is more narrow, which tracks. That makes sense because, again, that 4, that a times x squared is going to make it more narrow, steeper than a regular x squared graph. But also, it took the vertex and moved it up 1 unit because of that c right there, the +1. Okay, so it did 2 things. It made it more narrow because of the ax squared right there, and then the c told us that it moved up 1, the +1 right there. Okay, and again, I'll talk about what these 0 means right now. So in the margin in our notes, this is the last thing we'll talk about for this section, okay, for today at least. One thing you're going to be asked about is what's called a zero of a function. Okay, there are two ways we can attack this, but I'll explain what it means first. A zero of a function literally means when the function equals zero, which I guess makes sense. Okay, when the function equals zero. So basically in this case, it's where I would take this g of x and I would replace it with zero. So I would say x squared minus 3 equals 0. Okay, it's basically solving for when y equals 0. Again, f of x being a fancy way of saying y. Well, what does that mean graphically? Because graphically, it's going to be a little bit easier for us because then we can just visually look for it. Graphically, it's basically looking for x-intercepts. Basically, where is it crossing the x-axis? Why is it looking for x-intercepts? Why is it looking for when y equals 0? When y equals 0 means it's gone up or down 0. In other words, when is it crossing this x-axis? That's essentially what this means. So when it's asking for the zeros of a function, it's asking where does it cross the x-axis? So looking at our two brief examples up top here, it is possible for it to cross the x-axis 0 times. This is an example that would have no zeros, no x-intercepts, because the parabola is completely above it, doesn't cross it at all. In this example, however, it's possible for it to cross twice. Okay, and in this case, you would have to zoom in like on big ideas or on your graphing calculator, Desmos, and you'd have to see like where did it cross the x-axis. And I'll go through a little tutorial on Thursday about how to do that. But for our intents and purposes, basically just identifying where it crosses the x-axis. Where's the x-axis? This one crosses twice. We'd be able to identify those values. This one didn't cross at all. It's also possible for it to only touch once, and that's only if it happens where the vertex happens to be exactly on the x-axis and the only thing touching the x-axis. We actually saw that in section 1 when all the vertices were on 0, 0. So again, just returning back to our solutions just to chat about what we saw. In this first example, if you were asked to identify the zeros, again, it's where it crosses the x-axis when y equals 0. So visually, I'd be able to identify those values. And on this one, for part B, since the parabola we graphed never crossed the x-axis, that would be no visible zeros. Okay, so that will be it for today for section 2. This is a 2-day lesson. We'll talk more about transformations in our following lesson on Thursday. So if you have questions, as always, feel free to email me.